Okay, stream's good. Let's get ready to... I was gonna say rumble, but I guess we're studying, so let's do it. reindeer. Hold on, let me grab that real quick. That shouldn't throw us off too much. Alright, I'm gonna get something to eat really quick, and I'll be right back. Okay, I'm back. Gosh dang, I hate eating in front of camera, I'm sorry. I feel so terrible. now become a Twitter addict. Horrible Twitter addict. Probably fries the brain, but it's a good mental reset, I guess. Emotional reset. Probably not mental, but emotional. It's just full of nonsense. Possum Daily. What's the other ones? Like nothing but yotes. Cats with powerful aura. It cracks me up. I'm going to try to make videos now, I guess, because I hit a really quick roadblock in the homework, and while it's the teacher's office hours, he has not gotten back to me. So we'll try to make some videos. I think that's my water. I don't know how it ended up all the way over there. I think I might have found the issue. Hold on. Nope. let's turn on the AT2020. Alright, don't look at this stuff. This is not real. Can't hurt you. And let's do some old-fashioned studying. The way they used to do it, ancient Roman days. Homework number 8. We can do some old school 9.7 and practice. I'll start with 9.7 right in front of me. This is going to be out of order. Whoopsies. 7's going to start with... How can they make it any different? The same thing. The same thing. Okay. Longer. Yo, wait, what happened to the camera? Oh my gosh. Back you, camera. I know what happened. I think. Right here. Can't shut off the other camera. It's really cluttery. Alright, I'm gonna move my hand here, shut off camera 1. Let's shut this one off. Good for now. Okay. Okay. The waiting for this is always so difficult, but I think we're good here. Alright. So here we have our basic figure. A, B, C. Get some distances here. This is going to be 18 foot, 9 foot, 9 foot. Easy. Okay. And what we want to know is we want to find AY. Oh. Recording then. Okay. Here we have a figure. This is 9.7, and this is going to be the force method. So yeah, here's our beam right here. We've got a moment at A, and between B and C we've got a force P, which is 36 kips. And we want to find AY, BY, and CY, and EI is constant. Okay, so what are the methods, or what is the procedure to solve a force method problem for a beam? First is find determinacy. Here we have figure n equals 1. Reactions is 1, 2, 3, 4. N is A, Y, AX, and then BY, CY, so 4 altogether. And then, what's this now? R is greater than 3n by factor of 1, so it's significantly, or it's statically indeterminate to the first degree. So we've just done step 1. Step 2. Remove a redundant support. Step 2. I'm going to pick BY, because you can have a beam with an overhang, but we're using, what is it even called? Just like values you can look up at the back of the book, you know, like back of the book problem, or whatever it's called, to find the forces in the beam. So we need to find common beams, and simply supported is a lot more common, I guess, than an overhung beam. Maybe it's all the same, but just I guess best practices make it a cantilever or a simply supported beam when you can. So remove redundant support, or in our case, B. So this is going to turn into we have two different ones here. We're going to have our real. Okay, so this is our real. Real loading. And then we're going to have plus with our superposition idea. Or redundant. Loading. Oh, okay. So there. Real and redundant, and what we're gonna want to find here is now our compatibility equation. So step 3 is gonna be compatibility equation, and what we want to say is that this displacement here of cutting through the paper like that of a delta B, this is still at point B, is going to be equal to this delta B prime here. Okay, so delta B is going to equal our original delta B here plus delta B prime. I guess we can call this not really delta B, we can call it B. The vertical displacement in B is going to be equal to the initial vertical displacement of the real loading plus the displacement at B of the redundant loading. That's all it has to be. So just for, I guess, clarity, I don't want to have two delta B's. So now that we know this, we need to find out what exactly is the original delta B, and then we have to find out what exactly is our this. You know, because we know it's there, but we've got these forces here and this force here, which is going to be our By. And what is this going to be? So if we look up what I guess a simply supported beam with a moment is, then we're going to get an equation. And then also if we look up a simply supported beam here with just a force down on it, we're going to get another equation, and those are the two forces we have here on this. And then lastly, for this is going to be our delta B for our delta B prime. We're going to have a simply supported beam. And I'm only drawing these as like figures. You don't need to necessarily draw these with one force in the dead center. And all of these are going to have equations. So for this one up here with the moment, let's look this up. I have it written on a paper, but I don't want to use the wrong one. Simply supported beam deflection formula. We're going to look this up. Here we go. So for a moment, it looks like it's going to be ml squared over 2ei. For a point that isn't at the very end or the very center, I guess, it's going to be pa squared 3l minus a all over 6ei. And of course we're going to have an overall L. I'm going to split this in half. Right where this load is, the long side here is going to be A and the short side here is going to be B. So that's how that figure looks. That's how we get this. And then for a dead center load, it's going to be PL cubed over 48EI. And of course now we can find these values knowing that EI is going to be constant. I'm just going to say all of these, it's going to be divided by EI across the board. And now we're just going to assume that the EI is taken care of, and we're just going to plug in our actual numbers. So our moment M is going to be in our calculator here. Yeah. Okay. This is going to be 90 times L, which is going to be 18 plus 9 plus 9 squared over 2, which is going to be take it back. It's 9 square root 3, sorry. My bad. Copied it wrong. There. Just worry about this now. Alright, sorry. So it's, yes, it's going to be ml squared over 9 square root 3. So now I'm getting 7482.5. And then for this next one, pa squared 3l minus a over 6. So we have a force P of 36 times a squared. It looks like that's going to be 18 plus 9. That's our PA. That's going to be times 3L, which is 36. Minus A, which is 27, I believe. Oh gosh, this could get bad quick. All over 6. I don't like that at all. I have written something down completely different. Hate using different formula sheets. So if I reenact this, geez, where did I even get that one from? Beam deflection formula diagram for this one. It should be the same. It honestly should be. So I'm gonna try to make this work. Is 18 times 2 is 36. That should be 3L. Seven E A squared. It is our A. Oh my gosh, this is cantilever. I looked up simply supported and it gave me a cantilever. Okay, that is why these are different. Oh my gosh, my mistake. Not really my mistake. I looked up the right thing, but Google Images brought to you by the wonderful search engines at Google. Alright, the correct one here is going to be P lowercase b. My deepest apologies. I was wondering why it was different. Like, oh, I must have copied it wrong. 3L squared minus 4B squared all over 48 EI. Let's do this one more time. And I believe the A's and B's are going to be the same. Jeez, you can really do this a lot of ways, can't you? Because I've got on here negative EAB L plus B over 6. That probably works too. I want to see if I can get this one though, not overcomplicate things too much, even though they're already overcomplicated. So 36 times E times B would be 36 times B. Is our B going to be... I would almost say that it's going to have to be switched A and B, here A and B. So I'm going to initially try it as if A was B and B was A. And we had an A of what, 27? So I'm going to use that as our B. Sorry if this is already super confusing. Times 3 times 36 squared minus 4 times B squared. I'm going to say 27 squared all over 48. No, straight up, it really is B. It has to be. Let's change this 27 to a 9. And it is. So you really do, you keep the same A and B. You just do 9 from this end. Really neat. That is genuinely neat. Alright. I was assuming that couldn't be the case, because it's just kind of weird to not use the A. I think every formula likes using the A, but there it is. We got 24,057. And then lastly, I don't know if this one's correct or not now. PL cubed over 48 EI looks like it's fine. Alright. E, we don't know this. Okay. So now we're actually going to have to use our compatibility equation to figure this out, aren't we? Boy. So what this is going to be is we know that B equals delta B plus delta B prime, but our delta B prime here can be broken up further into being our reaction at By times an F of, I'm going to say B. And this F of B right here is going to be equal to that there. So we can actually say that this is, except for the P, this is going to be By times an L cubed over 48. Now, the only unknown we have is our by here. And we know that this plus this is going to be equal to this. So using our compatibility equation, we can say that by is going to be equal to 7482.5 plus 24057 divided by 36 cubed over 48. Let's see if that's true. I like saying that things are true and then figuring out if they are later. It's like my favorite pastime. That, and then we're going to do 36 cubed over 48. This divided by this. We're getting a by of 32.44. And if I plug this into yep, that is correct. Okay, 32.44 is all good. Now that we know this, we can use the sum of the forces here. We might actually need to do the sum of the moments first. I'll just do some of the moments right here under that. Moments about A. Since we know by and we don't know this one. We could also do C, doesn't really matter. But from A, we're going to have 18 negative 18 times by, which is 32.44, plus, because, wait, it's going to be minus as well. Minus 36 cy, and then of course that would mean that cy is going to equal 18 times that divided by 36, 16.2. No. Of course it would not be. Oh. We've got this 36 here. We aren't doing it on this fictional nonsense one. We are doing it on the actual figure up here. We're taking the actual moments on the real deal. $18 plus 9. This is going to be plus times 36 minus 36 cy. Here we go. We take this number right here, I'm going to add to it. Well, actually, that's a negative number, so we're going to negate this number. And then we're going to add to it our 18 plus 9 times 36 and divide that by 36. I still don't think that's right. Why wouldn't this be right though? 18 times by 18 plus 9 minus 36. And then the whole thing for CY. Adding these, and then it's gonna be the same thing. Oh my gosh, that's why. Because it's so freaking stupid. Oh my gosh. Because we're taking the moment about A doesn't equal 0, this equals 90. So now we take our moment here. Oh gosh. What does this mean? This means we're going to have a negative 18 times our 32.44 from up here. We're going to add to that 27 times 36. And now we're going to have a 36 CY. What we could do here is we could actually do minus this divided by 36 be 90 divided by 36. It is 90 plus. The answer is 13.275. Yes. Oh my gosh. Alright, so let's work backwards now. How did I get to this? Mental gymnastics and being wrong 100 times. That's how. We've got this big number here. We know that this eventually is going to be equal to, what did I get to? 300, so we had 387.935 minus 36 CY equals 90. Adding everything over to the other side should be 90 minus this. Did I assume the wrong positive here? They want it to be clockwise, don't they? Because if that's positive this way, then this 90 is also positive, so yeah. It can't be 90 because when you divide this by 36, it doesn't give us 13.27. You have to do 90 plus. You know, it works out if you do this the other way. If you actually take the moment the other way, it works out. If I take the moment to be this, that's positive, that's negative, that's positive, and what we get here is 18 times our 32.44 minus our 27 times 36. We get this 90 yeah. So I guess I assumed the moment to be in the wrong direction. Whatevs. Okay. CY is going to be equal to 13.275 This is where I would redo the video. But I'm gonna chug through this just for my own benefit. Now we can do some of the forces. NY, AY, plus BY of 32.44 minus 36 plus CY of 13.275. AY is going to be equal to 32.44 plus 36 minus 13.275, 9.75, negative? .72. Yeah. I'm trying to fix my moments. I've been taking my moments always this way is positive, but it seems like in this class they want this way to be positive, so me switching moments up is not the greatest thing when I've only ever done them one way. Should be all the same, but guess not. Guess not. So yeah, that's all the stuff we needed to find here. I would like to figure this moment out right here. This has tripped me up beyond anything you guys can imagine. I think that the moment should be positive in this direction anyway. And we've got 18 negative. So 100%, this is going to be negative 18 times 32.44. We know this to be true. Now we can move on. So that's going to be negative 583.92. And now we know that 27 times 36 is going to be positive. I'm going to add 972. And then we know that 36 times CY is going to be negative. What does this give us? this plus this. We have 388.08 minus 36CY is going to be equal to 90. Elementary school math. 90 minus this number, negative 36CY equals, this is negative 298.08. Divide this by negative 36, and we get the wrong answer again, 8.28. It doesn't make sense to me. I know this to be true. We have a moment positive in this direction, so anything going against it is going to be negative. 18 is true, and 32.44 is true. So this is a fact that is a negative 583. 18 plus 9 is 27, and it is a 36K force in the positive direction. So 27 times 36, 972. I know this to be true. We go all the way. 18 times 2 is 36. 36 is true, and I know CY is going to be pushing up. So that up force is going to be going counterclockwise, so I know that this is a negative 36 CY. Everything up to here is true. When you add these up right here, this could be a mistake. Do these add up like this? Or do they subtract? Because that's a positive number here, I think that adds. And it wouldn't really make any sense if it subtracts, would it? If I subtract that number, we get an absurdly large number. And 90 minus this, subtracted by 36, we're going to be way off. There's nothing we can do. This is added. But now that I know it's added, this number here, I know is true. Of course, if this was a negative 388.08, and we do 90 minus by that by 36, that gives us the right answer. But we would only ever get that to be negative if we took the moment in the other direction. Unless this moment here at 90 is negative, then what would we have? We would have our 90 negative here, and then divide this by 36, we'd have our right answer. So then y at 90 positive? Well, I figured it out. Because it doesn't equal 90 right here. This plus 90 equals 0, and it equals negative 90. Alright, found it out. Jeez. What a train wreck. Set it up. GG, go next. 9.7. Okay, force method. Looks like there's already a big air through this. Huh. Alright. We're all set up and ready to do this all over again. 7 minutes. I don't think I can do this in 7 minutes. And I can't do the next homework because I'm stuck and the teacher hasn't gotten back. Gosh dang. So I should probably just do a break early then. It would throw off my overall time schedule, but why the heck would I sit here and do nothing? Alright, we're gonna take a break early. How it is. Early break. Hello. How's it going? It is one of those days. It is oh show. One of those days. think today I just have a heart attack. But knowing my luck, I would have a heart attack at the end of the day instead of skipping the rest of the workday. Oh gosh. One of those days, man. Hourly Yeen. Best Twitter account ever. Antidepressant content. Oh gosh. They're feeding a cat a shrimp. Cat doesn't even know what to do. Look on account. Tomorrow live time? I might not be streaming tomorrow. My sister has to move. I might be helping her move. But if I can, I'll try to fit some streaming in. I just don't know when. It might be early, might be late. This is, hold on. I'm gonna mute the break timer really quick. This is why Twitter is the best. Just a, not a raccoon, sorry, a hyena. End of the day, Raccoon, welcome, you've come a long way. He'd probably say in that handsome voice. What does that mean? This is an awesome account, though. I have to follow it now. Alright. Best not dwell on that too long. See, it lightens the mood, though. So let's study. Let's go. Okay. Alright. Here we have problem 9.7. This is going to be a force method problem. Now, let's see, how do we tackle force method problems? Well, there's a procedure for all of this. With step 1 being to find the determinacy. For beams, we're going to have an n of 1, since we have one beam. And let's count the reaction forces now. We have 1, 2, 3, 4. 4 forces, A, X, and Y, and then B, Y, C, Y. So now we know that R is greater than 3n by 1. So it is statically indeterminate to the first degree. So now that we know the determinacy, step 2 is we have to remove a redundant support. In this case, B. We want to remove B so that we can make this a simply supported beam instead of an overhanging beam, which I'm sure would also probably work, but we want to make it either a cantilever or a simply supported beam. So now that this has a B fictionally removed, we can draw this with our method of superposition like this. Here, A. See, there's still B here, right? Here's our real force of 36k and our moment of 90 feet. And this is going to be our real loading. And with our method of superposition, we know that we're also going to have a redundant loading right here. Now we have a real and redundant loading. These both together add up to this. This is going to have a deformation up here, kind of like this, and this one, oh sorry, the other way. And this one's going to deform upward, like this. My apologies. We're going to have a deformation here of delta B, and a deformation here of delta B prime. Not the best way of showing it, but I think you guys can not really see it anyway, so double my bad. So now we can write our compatibility equation. With our compatibility equation, we know that this beam right here, I'm going to try to draw it really bold so you guys can see. This deformation here is going to be equal and opposite to this deformation here. So our deformation is B is going to equal our delta B from our real loading plus our delta B prime from our redundant loading. Okay? And of course that's going to equal 0 at the end. So now all we need to do is find out what is our delta B from our real loading, and then what is our delta B prime from our redundant loading. So with our real loading, we have a beam with a moment on the end. So with this, we know that the equation here is going to be, so for a simply supported beam with a moment, it's going to be, we can call this delta B1 for our moment. Doesn't really matter. It'll be M L squared over 9 square root 3 EI. And I didn't tell you, but I'll write up here that EI is constant for this problem. We don't actually have an EI. We just know that it's the same. So we can figure this out, and we're also going to have a second delta B, because we also have a force here, 36K. So what this is going to be is this one's going to be PB times 3L squared minus 4B squared all over 48 EI. And then of course lastly we have our delta B prime. And we're going to say this is divided by EI. This is also divided by EI. And that this will also eventually be divided by EI, since all these have EI at the bottom here. We know that this is going to be, what is it, PL cubed over 48. EI. If you're wondering how I'm finding these are known equations for generic beams. Like for this one here, it's a centered force load right here on a simply supported beam, so pin, roller on both ends with a load directly centered. That's what this equation represents. Similarly, this represents the moment, and this represents a force that is to one side or another of a simply supported beam. Okay, with all this, let's start plugging things in. So what we have here is an ML squared moment is 90 times an L squared, and L is 36 squared, divided by 9 square root 3 EI. So this is going to be 7482.5 over EI. Here we have this load right there. The force of this is going to be 36 times 9, because here's our A to here, and then here's our B to here. So B's length is 9. So BB times 3 times 36 squared minus 4 times 9 squared all over 48. 24057. And then lastly we have this force here, which we don't quite know this. So there's actually going to be a little intermediate step here. This force P is unknown. We can write this as By times L cubed over 48 EI. We know this is an L of 36, so we can also kind of write what that is really quickly. 36 cubed over 48 is going to be 972. So really quickly we can just say that's By times 972. And then using our equation here, we know that this plus this equals 0. So we can solve for By. So By is going to equal, this is going to be skipping a very small step, this plus this equals 0. So when we divide this by this, plus this right here, divide this by this, then we should get By. 7482.5 plus 24057 divided by 972. We're getting a By of 32.44. And you'll also notice that this is divided by EI, and this is divided by EI. So in the end, EI's cancel out, and what we are left with is just this. I'm assuming this is in kips. Okay, So now we have our first answer for AY, 32.44, I'm going to write K. Now, to find BY, sorry, that was BY. $32.44K for BY. Okay, now we're gonna use what we have figured out here. We know BY up here. We can now take a moment about A to find our CY and then use the forces to find AY. So really quickly right here, we can just say that the sum of the moments about A are going to be in this direction 90 minus positive minus 18 times BY plus 27 times 36 minus 36 times CY equals 0. Now let's try to solve this. So what do we have? We've got a negative 18 times 32.44. Here, should probably center this. Alright, and then we also have plus 27 times 36 here. That gives us 387. So now we can do 90 minus this. I think that should be 90 plus this. I think that should be 90 plus. Yes, it should be 90 plus. Why is it 90 minus? I have it on a little piece of paper here. Well, here's what I did, I guess. So we're actually gonna leave 90 out of this for now. I think I come back to 90 in this other way, and I think then it should be fine. So now we know that these two added together is going to be 387. So I'm going to say that 387.935 minus 36 CY can equal negative 90. Now from here, it's going to be negative 90 minus this. We have negative 36 CY equals negative 477.935. And then of course divide each side by negative 36. And we get our CY up here to equal 13.275. Okay. Here we are. So yeah, now we know our CY. Beautiful. Now we just do the sum of the forces, and now we can find our AY. So what we have is AY minus BY, or plus 32.44 minus 36 plus our cy of 13.275 is going to equal 0. So now we just subtract all of these to the other side, and that'll leave our ay alone. Ay is going to equal negative 32.44 plus 36 minus 13.275, which is going to equal negative 9.27. Alright, now we have our ay, by, and cy. Now the last part of this is, I think, probably going to be the trickiest, because it also asks us, there's a rip, to make this a little bit difficult. Ah, I got it. Alright. It asks us to draw the shear and moment diagrams for this. This is still 9.7 force method. And don't forget, this is our structure here. There. A, B, C. And we need to draw a shear and moment diagram. All the way to the bottom. Alright. This is going to be our shear. It's going to be our moment. And we can probably lightly just jot down where B would be. Just like that, just as a rough outline. Okay, so to plot our shear, we know that our AY, we can just write this right up here, AY, BY, CY, negative 9.27, 32.44, 13.275. Alright. Knowing this, we can say that our point here should start right there. This is going to be negative 9.27. It's just going to go over a straight line until it hits B. And then from B, it's going to jump up 32.44. So we're going to take our negative 9.27. We're going to add to it 32.44. That gives us 22.7. We're going to take this. We're going to go all the way up. There. This is our 22.7. And then, oops, there's our 36, or 90 feet, forgot, this is our real problem, you know, so we need to have these, we're going to come over there. This is where we have our 36. We're going to subtract from this 36. And this will get us to negative 13. What is it? 1.275. And then, of course, lastly, we come over. Boom. And then we're back up to 0 with our CY. So we've got this area here, this area here, and then lastly this area here. So this is going to be minus, positive, minus. Alright, now, what is this area here? It's going to be 18, 9, and 9. We're going to have an A1, A2, and an A3. Area 1 is going to be 9.27 times 18. Area 2 is going to be 22.7 times 9, and area 3 is going to be negative 13.27 times 9. Let's see what all of these equal. 9.27 times 18, negative 175. 22.7 times 9, 204. And then lastly, 13.27 times 9 is going to be negative 119, roughly. Alright, starting with our moment here, we have a starting force of 90. This is our shear diagram. Here's our moment diagram. Starting at 90, we're going to go down 175. So 90 minus our 175 will bring us to 85, down to negative 85. So doing this, that's our negative 85. Then we go up shortly, which is 204 plus our 204. Brings us to 119. Quite steep indeed. About there. 119, and then we're going to come down right here, negative 119. Okay. And there we have it. We have our bending moment diagram here and our shear moment diagram there. Yeah, that's pretty much the problem. I don't know what to do now. I don't know what to do with my hands. Thanks for watching. Okay, that was just the video. I'm still streaming. I had to say thanks for watching. Alright. So that's one. For beams, I'm going to do one for frames and then one for trusses. source method. Again, I don't think I can do this one in 24 minutes. Probably take a break early. Okay. Those are the things we need to find. This is a terrible streaming method. It's not 50-10 study with me. It's random and sporadic. Not good. I don't want to do this again this way, at least. Alright, I'm gonna take the break early. Low break people. I do apologize. I'm not gonna stream like this again. Gosh. Howard B. Yee. just to there. I'm gonna get there. Need directions. Is that what they say? People have to have direction in life? If mentally they're not all there? No? I'm really freaking scared about all this AI stuff, man. It's scaring me. All I gotta say. I can never tell if things are freaking AI anymore. Like this video clearly is, but I don't see no Sora watermark. Making it so you can't believe nothing that you see. This is awesome though. Possums every hour. See that? Awesome. Does put a smile on my face. I'm following him. How the heck do you subscribe to someone? I don't even know if it's a thing. I ain't doing it. On Twitter. Yeah, I've been wanting Oreos. Just have been. this is... I keep sharing you guys the memes. That's fun. That's really funny. United States Army Esports? What the heck? I know what I'm doing in the army, gosh dang, sign me up, son. Be the coolest thing. I mean, it's kind of really, really funny, but imagine, like, people are actually doing, like, war stuff, and you're like, nah, I'm on the esports team for the army. What the heck? Oh, that's funny. It's cool, I like watching these. It's, logging competitions and stuff. Oh, Poland's pretty good. Hold on, I just... Nope. This is the meme. Poland's actually really good at these. Don't make fun of the Polish. Okay, that's funny. It's funny. Okay. On to the next stream real quick. Let's go. It's probably my last one. So let's make it with it. Let's go. Alright, we just did a beam. Now let's do a frame. Okay, here's our frame. We've got 10 kilonewton per meter force here, 20 kilonewton meter force right there. And we have our lengths for BC, lengths for AB. And we want to know what AY, CY, CX, and MC are. And then lastly, we want to draw a moment diagram, a shear force and moment diagram for this. So let's get into it. So how do we do anything at all for the force method? Well, we have to first find determinacy. Okay, because this is a frame, I think we still do NR and all that stuff. So we have our NR1 until the frame has loops, then it gets tricky. R is equal to 1, 2, 3, 4. So we know that R is greater than 3, and so that this is statically indeterminate to the first degree. Okay, sweet. Step 2 is remove redundant. Technically, you can do multiple things. I think you can make this a pin and a roller, but that wouldn't give us a free end. Because if we just remove AY, it's still a cantilever beam, kind of. You can think about it like that. And then we can find the vertical displacement in AY. If this was a pin and roller, I don't even know how I would do that, but let's not, because usually when it comes to problems like this, you can just remove a support, you know, like completely. That's kind of, instead of simplifying a support, you remove one. I actually don't know if making it a pin would work. I think it would, but I'm just going to remove A. So now that that's removed, what will we have? Well, we are going to, I'm going to draw these simply. We're going to have a real loading. There's our 10 for 20 kilonewton per meter. And that's it fixed right there. Plus, we're going to have a redundant loading with force AY here. That's our fixed end right there. A, B, C, A, B, C. Okay. And as I've said, this is our real loading. And this is our redundant loading. So, lastly, we want to do our compatibility equations. So what is this going to be? Well, we're going to have a deformation that's going to look a little bit like this. It's going to come up and bend a little bit, and then it's going to come down here. Oh, sorry, the other way. The other way. No! It's going to come down this way. Just a little bit. And bend up here, and then this one is going to come upward and come back down. Oh my gosh. Oh my gosh, remove this one. This one never happened. And oh, I really screwed that one up. Done that twice now. Okay, so here's our 20 kilonewton. That's our beam here. And then right there is the displacement. So here's our A, placement at A, and then right here, similarly, this is our displacement at A prime. Okay, so this is going to push it down, this is going to push it up, essentially. So that we know that overall A is going to be the displacement at A plus the displacement at A prime, and that's all going to equal 0. Alright, now that we know this, what's going to be our displacement at A? What's going to be our regular nonsense? I'm actually, ooh, we ran out of paper. It's fine, because I can do this. Boom, hopefully you guys can see this. I'm actually going to tear this, so I can quickly come back to it. RIP pencil. I only do that so many times with these Rotring 600s. Kind of fragile to being dropped. Okay. What we're going to use is our principle of virtual work. Okay. With this one, we're going to have a P system and a Q system. We're actually going to have, I think, 3 principle of virtual works. We're going to have a Q system 1, a Q system 2, or no, a Q system and then 2 P systems, sorry. 2 real, 1 redundant. So I'm going to start with our Q system. And this here is going to be our virtual. System. Okay, so for this one, here is figure. That's our P prime is equal to 1. So with this, what are we going to have? We're going to have an x here. So that's going to be our x1. And we're going to have an x here. Okay, that's going to be our x2. And for frames, as it usually goes, we're going to have to do our moments and shear for M1 and M2 and all of this stuff, but we know that there's a P prime here, so what we can now draw is our, say, for x1, we have this here. These are the moments. Okay. This is going to be m, little m, 1, and m2. Or I guess it's just m1, which is just going to equal 0. I don't think there is an m2. This is just for x1. Yeah. Yeah, that makes sense, because there's nothing on this end. There's nothing. This is free. It's a free end. Okay? And I'm taking my jacket. This is really hot room now. For x2, I'm going to have this. A little bit. There. It is x2. So now it's going to be our m2 right there, finally. And we know that this distance here is our x2. So m2 is going to be a force times distance. We know our force here is p prime. P prime is pushing up on this right here. It's equal to 1. So our moment here is going to be 1 cross x2. Which is going to be 1 times x, which is just going to be x. Okay, so that's our Q system. Now we're going to have a P system 1 here, which is going to be our real system. And it's going to look like one of two things. Okay, we have all of our forces here. We have all of our forces here. So we have our 10 kilonewton force and our 20 kilonewton force. Because this is a principle of virtual work, I think we can only replace one at a time. So we're going to have to kind of use principle of superposition or whatever it's going to be called to say that this plus this is going to be equal to both of them. So for our P system 1, I'm just going to say arbitrarily that that one's going to be the 10 kilonewton per meter force here on the real system. Okay, and similarly again, we're going to have our x1, our x2 here and here. So 4 x1 here's our in here. Goodness me, I keep on cutting right through this. That's why I have a Kuratoga right there, but I'm not using it right now. This feels better to write with, and it isn't slicing through everything you're trying to draw. Alright, what else? And we know that that's x1. That's our moment. I'm going to make this a big M, because capital M for the real system. So this one's going to be M1. That's going to be equal to, remember that's 10 kilonewtons per meter. 10 kilonewtons per meter times how many meters of x? It's going to be 10x. I think that's going to be, for this moment, it's going to be 10x. 10 kilonewtons per meter times 1/2 x. Because we can say that this is a point load force right there halfway. We can say it's 10 kilonewtons per meter. Halfway down is its point load force right there. So what this is then equal to is 5x squared, and then for x2, here we have this here, remember x2, but this is still going to be the 10 kilonewton force there. What we are going to have for this moment is big M2. This is going to be it's 3 meters. 10 is 30. It's a force of 30, and it's going to be 3 over 2. Which that's now going to equal, move this here, 30 times 3 over 2, it's going to equal 45. Okay. If you want to know how it's 30, this is 10 kilonewtons per meter times 3 meters. And the force is acting halfway across the 3 meters, so it's 3 over 2. And that's the force that's causing a moment at M2. So that's how we get 45 here. And now, for our P system 2, okay, this is another real system. But this time, it's going to be the 20 kilonewton per meter here. Okay, of course, x1, x2, still same coordinate system. We have to keep it consistent from here to here to here. It has to be consistent. So now, for x1, we are going to have a system like this. Whoops. Pardon me. Gosh dang, I was drawing x2. No, we're going to have a system like this. We call that M1 as well. So for this, we're going to say that this is equal to 0. There's no forces. No forces acting on this. Okay, nothing to cause a moment, certainly. And then for x2, now we have this system. Alright. So now in this system, it's probably my... Okay, he did get back to me with that. I'll have to see that. Look at that in a moment. Okay, here, what we have is, because this is of course our x2 here, at 20 kilonewtons per meter, this is going to be 20x over 2, which is going to be 10x squared. Okay, now that we have all of these, I'm actually going to erase this, give myself some more space really quick. And these, we can quickly do some calculations. Now, up here, I'm going to write it. Remember that our P prime equals 1 delta A is going to equal the integral of L little m big M over EI dx. Okay, that's one of the equations that we need to know here, and then the other one is the F for A is going to equal, similarly for the P prime equals 1, F of A is going to be little m squared over EI dx integral to L. Okay, with both of these, now we can just quickly find our delta A and our F of A. So, delta A is going to look like M and M. We can just do for all of these, and then, yeah, just M1, 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 M2, M2, M2. We're going to have summation from 0 to 3. For x1, it's going to be 0. This is going to be over EI, and then this is going to be 5x squared. Of course, it's 0. Plus summation from big M over here, 0, 0 over EI, 0 to 3. Okay, it looks like that is just going to give us 0 for this. But that's also going to be plus from 0 to 4 of M2 now. This is going to be x times 45 for EI plus 0 to 4 of x times 10x squared over EI. So what this is going to turn into is going to be, of course, these are 0. This is going to be 45 over 2x squared, 22.5x squared. And this is going to be 10 over 3 x cubed. From 0 to 4. So now we're just going to plug 4 in. So 22.5 times 4 squared would be 360. I'm going to just write it next to it so I can have room for the next one. 360, and then 10 over 3 to the 4th cubed is going to be 640 divided by 3. Hold on. It should be 640. This should be 640. Oh, it's to the 4th. It's over 4. Yeah, okay. It's because that's 4th, it's actually 10 to the 4th over 4, so then that equals 640. So now you know that this whole entire thing is going to be equal to 1000 over EI. Okay, good. Now let's do f of a. Little f. A is going to be similarly, it's just going to be the little m's, right? M squared, so it's going to be 0 to 3, 0 squared over EI plus from 0 to 4 x squared over EI. So this is going to be equal to x to the third over 3, which is going to be equal to 4 to the third, 3, 4 to the third over 3 is going to be equal to 64 divided by 3, which is going to be equal to 21.33. So that's going to be our delta A. That's going to be our little f, a little violin hole f, a. So now, with these, we know that A is going to be equal to delta A plus AY delta FA equals 0. With all of this now, we know that AY is definitely going to be equal to delta A divided by little f of A, which is going to be equal to 1000 divided by 21.33, which means that our AY is going to be equal to 46.875. Yep. Okay, now we know it's equal to 46.875. AY, CY, those have to equal 0. We have 20 kilonewtons per meter times 4 meters, that's 20 times 4, that's 80. So 80 minus 46.5, we know our CY should then be equal to, so if we do some of the forces, in Y, 46.875 minus 80 plus CY equals 0, so now we know that our CY is going to be equal to 33.124. Okay, so now we have this, 46.875, 33.124. What's our CX? It's going to be 10, it's going to be 30, negative 30. Wait. Yeah, it is, negative 30. Because we have our 10 kilonewtons per meter here, times 3, that's 30 this way, which means our CX has to be 30 that way, which is the opposite of this one. So it's negative 30. I can show you some of the forces, but I just explained it right there. 10 kilonewtons per meter times 3 meters is 30. But this CX has to be the opposite of that. Now we have our 3 there. We have now to find the moments. So sum of the moments about C is going to be equal to 20 kilonewtons per meter times 4 meters, as stated was 80. We're going to take this to be positive, so 80 times 4 divided by 2, so it's going to be times 2. And then it's going to be minus plus, it's going to be 4 times AY. AY is 46. We need some 5. Now we just have to figure out what this is. 80 times 2. So it's going to be negative 160. Oh, whoops. Negative 160. And then we're going to have 4 times our 46. So add these up. 27.5. Whoops, something's wrong. Let's take a step back. 20 times 4 is 80. 80 times 4 over 2. 2. And it's going to be 4. Ah, we're forgetting our moment right here. 10. 10 causes a moment. And it's causing a moment this way. So it's going to be minus 30 times 1.5. Alright. 30 times 1.5. So we're going to have this subtracted by this. MC is going to be equal to 17.5. Okay, and this is going to be kilonewtons per meter. And the rest of these are going to be in kilonewton. Alright. Now the last thing to do is draw the shear and moment diagram. Okay, it's going to be shear, it's going to be moment. Alright. With this now, we can say that AY is going to be 46 up here. 46.8. And it's just going to go down. It's just going to go down from there until it gets to 33.124. It's going to jump up. Hold on. Yeah. My apologies. We're going to have two shear force diagrams. This is going to be for x1. It's going to be for x2. Luckily I was going to do it space-wise, but this actually works out too. So VM, the 46. It's going to come down here. Okay. Let's just make these bigger. A little bit sloppy, but it should work. Negative 33. Yeah. We have E1, E2, and then we're going to need to make a moment diagram out of this. Okay. We need to find what A1 is equal to, and we need to find A2, and from there, we figure this out. This is actually for x2. So this one's going to be for x1. Oh my gosh, I'm all over the place at the end here. And I'm changing things on the fly. Okay, so this is x2, this is for x1. We can quickly do for x1 here. We're going to have 10 kilonewtons per meter times 10 meters. And then it's going to eventually have to be cx, so negative 30. So we can just start here. Say right there is negative 30. This one's going to be really, really easy. Oops. So there. It would be 1/2 base times height. The base is 3. Height is 30. One half 3 times 30 is 45. So now we know that for this, if we remember our order of lines, looks like this. Okay, this is a Jeff Hansen idea. Because we just had, whoops. Because we just had one of these, it's gonna have to be parabolic, and it's slow then fast. So this one here for moment diagram here, it's gonna be slow then fast, and it's gonna end here at 45. Okay. So there. this is for x1. Now for x2 here, we're going to have two triangles. This triangle here, and they equal this triangle here. So this triangle here is going to be our 46.8. And this is going to be our x, and then this big triangle here is going to be, well, what was the distance down that it had to travel? The distance down that this had to travel was, let's see, 80? If we do our 46.8 and we subtract 80, that gets us our 33, roughly our 33.125. So, I'm going to say that height here is 80. And then the distance here is our distance up here, which is 4. So now that we know that x is to 46.8 as 4 is to 80, we can find out that our x is going to equal, which is our distance here, that's our x, is actually going to equal, let's see, I want to get our exact number, that's 33.125, where's the 46? 46.875 right there. Okay. We're going to multiply 4 over 80 times our 46, which means x equals 2.343. So now we can get our a1 and a2. a1 is going to equal, and then a2 is going to equal, let's see, 1/2 our base of 2 point whatever that is times our height of 46.875, getting 54.93, and then a2 is going to be 4 minus this 2.3, which is 1.65, so it's going to be 1/2 of this times our height of our 33. We can quickly scroll back up. This is our 33 right here, 125 or 1249. So here we're going to have 27.43. Those are our areas A1 and A2. So now for our moment diagram, we do have to remember, however, that we have moment CX. How the heck do I get this here? 45 right here. So it's 45 here at the end of X1. So at the beginning of X2, we have to likewise start down here at negative 45, okay, just as this was, and then we're going to go up, okay, negative 45, so negative 45 plus 54.93, this gets us to right there, 9.9, right at that turning point, and this is fast then slow, so it should look like that. And then we're going to do the opposite, slow then fast here, and this should get us to our A2 of 27, so we're going to do 9.9 minus our 27, which is going to be 17.5. We come here, we go down to there, which is negative 17.5, 9.9 minus our A2, and then here we have our bending moment diagram, shear diagram for X2 and for X1. I wish I did them this way, but they're swapped, so that's X2, that's X1, but it's all entirely true. I know, because I was there. So yeah, there's all the work. Hope you guys enjoyed. Peace. Oh my gosh, I almost died. Oh, that problem almost killed me. Oh my gosh. And in lieu of our break, I am just going to end the stream here. For real, this is the stream this time. I want to thank you guys for watching the stream. catch you guys again as soon as I can. So,